ready to go through some SolidWorks flow. I'm going to show you kind of a tutorial on quick tutorial on how to use SolidWorks flow with this tank flow problem. I'm Dylan Pratt. I'm the Director of Engineering here at InterLink. Been doing CFD for about 5 years or so. Most recently with SolidWorks flow, but I've used a handful of other programs. And I've been using SolidWorks in total like 15 years. So got a bit of experience anyway. Now, you might be asking yourself, what is CFD? This is the quote unquote textbook definition, but the best way to think of it is trying to analyze fluid flow or predict how fluid will flow given certain circumstances. So essentially mathematically defining how the expected fluid will flow given parameters. Now, what types of problems will you be able to attack with CFD? You're going to be looking at using gas or fluid or fluid. So there are problems where you're going to be really analyzing both the interaction of your gas and fluid. But you might just be looking at fluid in a pipe. That would be something like an internal study, or an external study would be something like, actually that picture is a pretty good example of like a car driving down the road. So it's more of a external effects. You're not just inside a tight volume. Now you could also, like I said, be mixing that water and gas. Maybe there's rain and wind on the external study, something like that. Now, just to give you an idea on timelines, I think that's something maybe often people don't talk about is, you might be looking at a few days to get all of your parameters straight, your models organized and ready. Often models need slight adjustments for analysis purposes, and like gaps filled and different things that might be manufacturing features, but for analysis purposes, it really complicates the analysis. So you need to go through, clean up your models, get all your parameters, all your known data down, so and then set up the model. So it might be a few days for that. You might have another few days for the actual analysis part to allow the computer to go through and print through your analysis, depending on how detailed you're being in terms of like mesh size and other things. So we'll talk about in a few minutes. And then on top of that, you may need an extra few days to process the data, because unlike we're all used to SolidWorks. If somebody asks us to complete a model, at the end of the day, we hand over the model. That's the product we're handing over. With CFD, what we're handing over is often data, or we need to gather the data and put it together in a presentation or a report like this to interpolate that data into an answer of a question. So you may have more time putting together multiple pieces of data, not just oh yeah, sorry, I'm getting to know I need to speak up for the room. I'll try not to yell, but turn me down online if I'm too loud. Anyway, so you might need an additional few days to process the data and everything for the report as well. So by the end, you could be looking at a week or multiple weeks, depending on how many problems you have. Sometimes multiple types of multiple instances need to be run. So it can add up in time. It's just something to consider. Now I'm going to use this project as just a quick overview of what you can do with CFD. However, here's some parameters we have. It's a tank with 156-degree water. We're going to assume the flow can be laminar or turbulent, depending on what the analysis dictates is necessary. And we actually do use a mixture of air and water, very minimally. So it's just allowing there to be essentially a pocket of air at the top, so that the fluid flow is more accurate. It's not an enclosed volume. It's not a sealed box or anything. It's an open air tank, so there is a little bit of air there to account for that. And then there's a couple other. The only other maybe important one I'll mention is we're not worried about friction on surfaces. You may know, that water it actually gets sticky depending on the type of material surface we're talking about in terms of the fluid flow. But really, the area in this case that we're concerned with is in the middle of an open tank. We're not going to worry about the friction. It's just going to slow us down. But you could, yes, good question. Yes, you could account for wall friction if you need to. All right, now let's look at the setup. I have pre-recorded a lot of, or really all my presentation, just so we don't have to worry about load times or something going wrong. So I'm just going to walk you through the recording. So here, what I'm going to do first is just hide my tank, because really all I'm going to be looking here at is the actual water body. So I put in a body that represents the water in the tank at the correct level of fill. We're going to run the wizard just for simplicities to set this up for you guys. I'm going to change the units to US, and in particular, I'm looking to change my flow rate to gallons per minute because I don't want to have to convert it. That's the flow rate I have. It's going to be 12 gallons per minute. And then I'm going to look at what is important to me. So like I said before, in this case, this is an internal study. We're just focused on the tank, not outside effects. We're going to consider gravity. And in this case, or in all cases, SolidWorks defaults to gravity in the negative X direction, but almost always have it in Y. So we're just going to change that over. I need to turn on my time dependency because we're going to be running this for a certain amount of time. I'm going to run it for about 30 seconds. But I can stop it early if I want to. And then free surface just means there's that surface between air and water. So we're going to need to include air and water. And that's what I'm doing now. I'm just going to select my materials, activate those. This is where I could set roughness for materials, but I'm just going to go ahead and leave that as 0. I'm not going to worry about outside heat sources. Is it just roughness? Just roughness that I can remember offhand, yeah. So here you can see the computational domain isn't including the whole problem, but we're going to set some parameters that will fix that basically. And here what I'm doing is telling my main body here that it's water, and then I'm going to tell it to disable this component for the study essentially, because it's not a true wall, it's not an object, it's the body of water. So we want to disable the component. It's a little counterintuitive, but it's just what it has to be. You got to disable it. And then I'm just telling it that it's water here and that it's at 156 degrees. The other thing I'm going to do now is set up some boundary conditions. So that's where the lids come in. I forgot to mention that earlier, but basically there are lids at the borderline between surfaces. So that between the outside and inside of your study, they're what we call lids. And that's what I'm doing here is I'm selecting the top surface of the water, or I'm sorry, actually it's top surface of the air basically. And I'm just setting that to environmental pressure. So this is just an open air tank. And then I'm going to select, first I'm going to hide that so now I can access my other lids, my interfaces. And so I'm going to set an inlet flow on these pumps. Now, in reality, what these pumps are doing is recirculating the water in the tank. It's a little difficult to simulate perfectly, and I don't want to have to simulate a propeller moving the water around. It's a lot of hassle, and it's not really what I care about in the study. So what I'm actually doing is essentially telling it it's pushing 12 gallons per minute of water into the tank, and then I'm at the same time pushing 12 gallons per minute out of the tank so that the water level isn't ever changing. It's essentially simulating circulation without me having to worry about moving around with a propeller or anything. In that case, also what I did there, sorry, I missed it while I was on the screen, but I set the inlet water at 158 degrees, just slightly above my 156. And that's so later you'll see I can better track the water flow in because I'll actually see the hotter water when I'm looking at temperature. Whereas if I just set everything to 156, I'd have to just base it on velocity vectors. It's much easier to see water flow through with temperature relations. Awesome. And then I set my outlet velocity, like I was saying before, so that there's actually water pumping through out, but it's not really going anywhere into the system. It's going out into a black hole essentially. And here now, when I reset the computational domain, you can see it's across the whole water volume. And now I'm just going to go through. We have all our parameters set. I'm going to go through and set the mesh size. Is what I'm doing here. Sorry, it's a little off screen for the people in the room, but I'm just setting basically what my grid mesh will look like. And then I'm keeping it very simple, no extra settings for this. And you know, again, just trying to get a simple baseline basically. So just keeping that pretty basic. And then once I have those mesh parameters set, I'm going to change a couple calculation control options. So I'm going to double check that's 30 seconds, which if I hadn't set it for 30 seconds, I could now. My time step, I'm just going to let SolidWorks decide what my time step is. Often I'll adjust that slightly if SolidWorks is maybe being a little over conservative and I'm just trying to get a rough look at something and I don't want to wait a lot longer for it to show me results. And then I'm going to just tell it to save periodic backups basically. So if something happens, my laptop dies or something. Sorry, 1 second. Kind of lost how I can pause it. Say that one more time. So I have the pump. So the question is like, how is the pump flowing basically? So the pump is flowing pretty much the way it does in reality. So there's a, and I'm sorry, I'm describing things with my hands for those online, but I'll do my best to point and click later to show you. But basically, there's an inlet down here on the bottom of the pump. And so that is where the inlet, that's basically where my outlet is sucking in there. And it's just going out into nothingness space for me. And then the outlet is coming down through the pump and out. So the inlets and outlets are behaving the way they would in reality. It's just we're not actually simulating the inside of the pump correctly. But for my necessary, or for what I deem necessary, it doesn't really matter for me. And I'll show you a little bit what I'm talking about here in a second. So, actually, wow. Yeah, no, I'll just stay here. Sorry, I wasn't sure if I was on the right page. So once we got those results, so once that started running, I just kind of showed you a quick snippet of that preview you see a second ago while it's running. You get, I'm sorry, so you get that preview, and then, but now we'll look at the results. And what I'm showing here is just the velocity vectors coming out of the pump. What I'm looking for is just the velocity vectors kind of looking to some degree logical. You know, there's nothing, no crazy offshoots or anything that to make sure that it looks, you know, the flow is quick coming out of the pump, and then as it's hitting this body of water, it's starting to slow down. You can also see kind of where the activity is primarily focused. And then what I'll do is show you the temperature plot. And this is why I set the temperatures differently. This view, you can see a little bit better what's going on. So the pumps are ejecting that water, that slightly warmer water here. But we're really only hitting kind of the top area section of this pump right now. And ideally, this pump would really, you'd split, or rather the tank, you'd split roughly into thirds, where each pump is sort of causing that turbulence in a different portion of the tank. But this whole area down here isn't getting a lot of action. You guys can't see my pointer, I apologize. Yeah, this whole area down here isn't getting a lot of action. So let's look at a design change. That's what we'll do now. So what I'm essentially going to do is to make a really simple design change. I'm going to hide my tank and just look at the pumps. And while we're looking at the pumps, I'll try and point out a little bit what I was talking about as far as simulating the flow without actually worrying about the propeller. So you can see that boss there at the bottom is the inlet to the pump, outlet of my system, basically, and then the other thing. So what I've done here is split my bodies. So I've just split the nozzle head basically so that I can manipulate it easily. So I've just moved the body and kind of rotated it so my nozzle head, the pump, it isn't actually designed this way. We'll have to do a design change to actually get a new nozzle head to accomplish this. But for my analysis purposes, I'm just kind of trying to come up with a quick way to be able to simulate a different head position and then, combine it back together and run another analysis. Then we can go to a design change to kind of limit our time and focus time where it matters. Now I would just go through the same steps I showed you before. I went ahead and just skipped ahead so you didn't have to see it twice. But it's the exact same parameters, exact same setup. The heads are just moved a little. So at this point, we can just hit run again. And in this case, I'll just skip to results. And you'll see we definitely have a more separated flow here. Everything still looks kind of the same as far as a high velocity coming right out of the pump before it starts mixing, causing turbulation in the rest of the body. But the heads are more evenly dispersed. And again, if we look at the hot water, you'll see now we really have that nice, relatively evenly split system where each pump is in a subsection of the tank rather than the all the energy being focused in one area, which is what we were looking for. And so in summary, yeah, basically, CFD can solve your flow and heat transfer problems. We just touched a little bit on the heat transfer part of it as far as analyzing different heat sources and stuff, but that's definitely a big part of CFD as well. And then, I'd recommend always trying to keep your changes small and iterate often is a good way to attack problems like this, because if you change, 20 things, you don't really know what had the largest impact. Often a small change, check it, small change, check it, rather than try to incorporate 20 changes at once. Will get you there faster, in my opinion. Are there any questions I can answer?
What was the concern on the reason for this study? Was it that they wanted an even mixture of tank?
Yeah. Yeah, good question. So he was asking why basically why do we care if the flow is even or not? In this case, basically there'll be other things. Right now I'm analyzing an empty tank. At some point there will be stuff in that tank. Objects that we actually want to be agitated essentially and cause a lot of it's for breaking down materials and stuff. So we want to cause a lot of agitation, but more specifically, we want to cause agitation where the parts are, and the user will actually have ability to control which pump is giving more energy, or if there may be a pump that's just off. Hey, I'm only putting parts on this third of the tank because I only have a couple parts maybe and not a whole tank's worth of parts. Oh, all right, we'll just run pump 3. No reason to run pumps 1 and 2. They don't even hit over there. They're not really causing that much turbulation. Or maybe I'll just run them on low and I'll run pump 3 on high because that's where my parts are. But if you had parts in the front, they're not even going to get hit, even if you had all 3 of them on high. Or even if you had parts in the back, you're not getting a good mixture. So yeah, no problem. Any other questions?
Don't see anything on chat,
Yeah.
Dylan.
Okay, perfect. Thanks, Bobby. Well, thank you very much for coming to our event. I'll move on to the next slide, actually. If you have any questions, please reach out anytime. We've got a SWUG email. And if you have any suggestions, we'd love if you have a topic you'd really like to hear more on, or have an idea of restructuring anything, or you want to be more involved in the group, feel free to reach out. Yeah, if there's anything else. Oh, we included some VAR information below for those of you that need to or want to get more SolidWorks or get SolidWorks at all for yourself. If you don't have it right now for yourself or your company, we included some VARs below. Some of them might still be on the line. I'm not sure. Hopefully they didn't mind. And yeah, if there's anything else, please reach out anytime. We're always here to help.